let's begin Chapter 9. Chapter 9 is on analyzing circuits with sinusoidal sources. So first we need to look at the sinusoids themselves. And this is stuff that you've seen before. You're just looking at it in a slightly different way. So section 9.2 is on the sinusoid. So we have some v of t equals Vm sine omega t plus phi or phi, whichever one you want to call it. So Vm is the amplitude, or our peak voltage. Our omega is our angular frequency. And that is in radians per second. And our phi is our phase angle. And that is in degrees. So that's a little bit annoying because we have radians per second plus degrees, but we also have the unknown t, right, which is the seconds. So if you're doing one of these and you have a known time t, then you have to change this to degrees or this radians to per second before you can add them. So just, pay attention to that. Period. The sinusoid has a period of t, and we know that t equal 2 pi over omega, so we can find our period that way. Or rearranging that, omega equal 2 pi over t, which is probably more frequently how you see it. And we can find our cyclic frequency, lowercase f, and that's 1 over t. So we use these in the lab, and these are equations you're expected to know. You should memorize these because you'll use them over and over again in this class and in other classes. All right, so let's look at some notes about sinusoids. We can have a phase shift phi, and it's equivalent to shifting time some delta t. So our omega t plus phi, we could say that's omega t, oh, sorry, that's not what I wanted to write. See if I can erase that. Omega times t plus delta t, so some time shift, our delta t, meaning that our phi is omega delta t, or 2 pi delta t over t. Just another way to look at that phase shift. So if we have a phase shift of pi over 2, 90 degrees, right? Shift by 90 degrees, then our delta t becomes t over 4. So it's a fourth of the period. Second note, positive phase shift is a shift to the left, so earlier in time. I think it's easier to think of it that way. Earlier in time, in other words, left. So that's when we have a cosine of omega t. That's also the same thing as sine omega t plus pi over 2, right? Because they're out of phase, so sine and cosine by 90 degrees. Or we can write sine omega t is cosine omega t minus pi over 2. And the third one, if I can squeeze it down here, is a phase shift phi is same as phi plus pi over 2, right? So if you shift a sine or a cosine, pi over 2, it looks exactly the same. So that's what that's saying. On the positive phase shift, let me get a different color here. to the left, we say that this is a leading phase shift. So we call that leading. When we have a negative phase shift, so later in time, we call that lagging. So again, terminology you've used in other classes that you've seen before. It's sinusoids. There's nothing shockingly new here. And we can represent these as vectors using vector representation. This is also in the same section. So if they have the same frequency, say sinusoids with same frequency, we can represent them with 2D vectors. So if I have some V1 that's 10 cosine of omega t, and a V2 that's 5 sine of omega t, well, I need them both to be in either sine or cosine, so I'm going to translate this one into cosine. So it's 5 cosine omega t minus 90 degrees. Then I can draw V1, 10. This is my V1. And I can draw V2. I'm going to go ahead and switch colors here for V2. So V2 has an amplitude or a peak of 5, but it's shifted by minus 90 degrees. So we say V1 leads V2 by 90, or we can say V2 lags V1 by 90 degrees. So again, that's just terminology and vectors. Hopefully you're used to doing those. You can add vectors, so it's just normal vector algebra from there.